let's go ahead and get started. So today's class we're going to be moving on to completely new material, and that's going to be concerned with what's called the work energy theorem and ultimately conservation of energy. So hopefully you've seen the videos that Professor Shepard and I have put out, but today what we're going to do is, to begin with anyway, is to kind of go over some of those concepts that were laid out in the video. And so something that you're probably finding is that this concept of force comes up again and again. We first saw it with Newton's laws to describe how something can get an acceleration or change in velocity. But we're going to see force in a slightly different way when we're looking at it in terms of the work energy theorem. We're going to see it again next week or the following week when we're talking about momentum. So force as a concept is something that's tied in with a lot of the things that we're going to be talking about. So to start out, I want to kind of define what's meant by the work energy theorem and how we can kind of conceptually think about that. So to do that, what I'd like to do is consider some box that's on some flat surface, and I'm going to apply some horizontal force to it, F. Now, we know from our studies of kinematics and Newton's laws that if I'm applying this force to this box and there's no other forces like friction acting on this is going to cause it to accelerate. So if I cover some distance d here, there's going to be an increase in its velocity, right? So when it gets over to this point here, we can call this the initial point, and we can call this the final point. This is going to have some final velocity associated with it. And so if this started from rest, of course, this is going to be increasing in velocity. So what we would have done previously was draw a free body diagram, sum the forces, find what the acceleration is, and then we can use that acceleration to find what the velocity is using the kinematic equations. But there turns out to be an easier way to do this, and that's to use what's called the work energy theorem. And so to define work, what we do is we say that the work is going to be equal to the force times the distance that force acts over, times the cosine of the angle between the force and the direction that this object is going to be moving. And so in this case, this is really kind of the simplest case that you can have. The force is moving in the same direction as this displacement that it has here. And so for this case, this says that this is going to be equal to the force times the distance. Another way that you can say this is that the work done by some force is going to be equal to the force that's parallel, so sometimes you put this parallel sign, to the distance that it's moved over. Okay. Now this is how we define work for the work done by an individual force on an object, but we can also talk about what the total work is done on this object. And so if I draw my free body diagram here, I see that there's actually two other forces that are applied to this. There's the normal force, the force of gravity, and this applied force I'm calling F. Now, if we calculate what the work is done by the normal force, for instance, we see that work is going to be equal to 0. Why should the work done by the normal force be 0? Because it's orthogonal. It's the angle between the displacement that we have in the force is 90 degrees. They're perpendicular to each other. So no work done by normal force. We can say the same thing for the work done by gravity, because again, it's perpendicular to the displacement. So what we can do when we calculate the total work on this object is we can say that the total work is going to be equal to what's called the change in kinetic energy, where the kinetic energy is defined to be K is equal to 1/2 mv squared. Okay. Now, because this is some change, really what this is the difference in the final kinetic energy and the initial kinetic energy. And so we could express this then by saying F times D is going to be equal to 1/2 mvf squared in this particular case, because we could treat this as if it started from rest. So this is kind of an outline of what's called the work energy theorem. And what we're going to end up building this into over the course of the class is the what's called conservation of energy. Okay. So just to kind of look at some examples of energy that we have here, we're going to talk about gravitational potential energy. So gravitational potential energy is given by mgh. We've already seen the kinetic energy here that I just defined. This is 1/2 mv squared. We have the spring potential energy. So if I compress some spring and I hold it compressed there, you say that that has the tendency to make something want to move. And it's really that tendency to want to move that we call the potential energy. The work energy theorem, here I said this is actually, as listed here, is not true. The work energy theorem says that the work is equal to the change in kinetic energy, not the change in total energy. So this is the work energy theorem. It's the change in kinetic energy. We also have power. So power is defined to be the work done per some time. And so when you talk about your electricity bill, you don't talk about it in terms of energy. You talk about the power that you consume. Okay, so looking at our spring, because I brought up the spring and we want to kind of think about the way that springs work, because springs are really important mechanisms in physics. When you stretch a spring, you say that this x displacement is positive, and the spring force is going to be directed to the left. And so to diagram this out to go with this picture that we have, so we have our spring, and it's at its unstretched length. Okay, and in general we apply what's called Hooke's law to describe the force on a spring. So this is going to be F is going to be equal to minus kx. So if I pull this spring, we know what should happen here. This should be pulled back to equilibrium. And so this equation holds the way that you expect it to, because if I define this to be x is equal to 0, then this is going to be some positive displacement. I plug in a positive number for x. This gives me a negative for the force. And so the direction of the force is going to pull it back this way. Now, when we look at the opposite case here, when x is negative, or when we compress the spring, so we have this case. This is x is equal to 0. Then this displacement is negative. And so if I plug in a negative value for x, I get a product of two negatives that makes this positive, and so the direction of the force on the spring is going to go this way. Okay? So when we want to talk about conservation of energy, the way that we can do this sometimes is to draw these bar charts to represent the conversion of potential energy to kinetic energy and vice versa. So you can look at this series of pictures that we have here. So in the beginning we have this block, and it's not in contact with the spring, and so there's no energy. This isn't moving. And then we can take it and compress it by a certain amount. We're still holding on to it. So when it's compressed like that, we're increasing the potential energy, which in turn increases the total energy. The second point here, I've compressed it as far as I'm going to compress it, so that has the maximum potential energy, and then I can let it go. So in the fourth panel, panel C, when I let it go, this potential energy is converting to kinetic energy, right? Because when I let it go, it's going to start to move. And so the motion is causing there to be a larger kinetic energy. But you see, when I add the kinetic energy and the potential energy together, I still get this red bar. So that tells me that the total energy is conserved, even though it kind of goes from potential energy to kinetic energy. And then when it leaves the spring, it's not in contact with it anymore. The spring's not compressed at all. And so all of that potential energy is converted to kinetic energy. Okay, so let's get into our first question of the day. And so this question asks, a person lifts a box from the floor. How would you describe the work done by the person? Would you say that this is positive work, negative work, or zero work? Okay. Okay, so let's talk about this one. So what do we think? Is this work going to be positive, negative, or zero? Positive. Why is it going to be positive?
They're in the same direction.
Yeah, they're in the same direction. So if I'm lifting something up, the force that I'm applying to this eraser is in the same direction as the direction of motion. So what would we say the work would be done on this object by gravity? How about somebody from kind of the middle back over here? What's the direction of gravity? It's in the minus direction, and I'm lifting it up, right? So these are in the same or opposite directions? Opposite directions. So what do we think that means about the work in that case? It's going to be negative, exactly. And the way that we can track that is we say, okay, well this work, really we can treat these as absolute values, and then the sign information is contained in the cosine of the angle. But if these are in the same direction, the angle is 0, right? Two things going in the same direction, there's no angle between them. But if they're in opposite directions, then the angle between these is 180 degrees. And the cosine of 180 degrees is negative 1, actually. So that gives you the negative work, okay? Now let's look at another one. So in this one, person carries the block across the room. How would you describe the work on the box by the person? Okay, so let's talk about this one. What did we say about this one? How about somebody kind of from the back over here, kind of the back middle? What do you guys think?
0.
0. Why 0? I didn't see who said 0. Yeah, a little louder. I can't hear you.
The angle that the work being done is at 90 degrees.
Right. So think about what forces act on, let's say this board that I have in my hand. If I'm not holding it up at all, the only force acting on it's gravity. And that points straight down, right? So by putting my hand here and keeping it in equilibrium, what I'm doing is I'm applying some normal force that's counteracting gravity. But if we want to move this horizontally, I don't have to apply any additional force to counteract. I mean, yeah, if we wanted to say we had to counteract air resistance, okay, we're ignoring that. Okay, everything we do, we tend to say we're doing in a vacuum. So I don't have to apply a force to make it go this way if I have it moving at some constant velocity, right? This is like Newton's first law. So because of that, what we can do is we can say that there's no work that we need to apply to move something horizontally. Okay. Moving on. So now we have another question here, and this one says a skateboarder slides into the grass and slides into the grass that slows the skateboarder to a stop. What sign of work is done on the skateboarder, and what is the work causing force? So you're going to have two answers for this one, for A through C, and then a second answer for, sorry, you have one answer for A through C and one answer for D through F. Okay, so go ahead and talk about this one. Okay, so let's talk about this one. I almost, because I was thinking I wanted to draw grass on here, so I almost grabbed this marker and drew on the board. That would be a bad idea. But we can still draw grass, and make it yellow grass, I guess. It's autumn or the grass is dying or something. So we got our skateboarder that's going to be moving into this grass. So here's our skateboard, because that's exactly what skateboards look like. And this is moving in here, and as it moves into the grass, it's going to slow down, right? So what we'd like to do is we'd like to talk about, first, what is the direction of the work, or sorry, work doesn't have direction, work is a scalar, but is the work going to be positive, negative, or 0, and why? So what do you think? It's going to be negative. Why should it be negative? What do you think?
Because it's a deceleration?
Yeah, you could say it like that. It's negative because it's deceleration. So we could go all the way back to the work energy theorem here, and we can say the work is going to be equal to the change in kinetic energy. Well, we have some final kinetic energy and some initial kinetic energy when we talk about the difference between these, right? So he's going to come to a stop. What does that say about the final kinetic energy?
0.
It's 0, which means that the work is going to be equal to the negative initial kinetic energy. So the work should be negative. Okay. Now, what is doing the work here? What do you guys think? Friction. Friction's doing the work to stop. Good. Okay. So let's move on to the next one. Okay, so now we're starting to do some calculations here. So for this one, it says early one October, you go to a pumpkin patch to select your Halloween pumpkin. You lift the 3.2 kilogram pumpkin to a height of 1.2 meters, and then carry it 50 meters on level ground to the checkout stand. calculate the work that you do on the pumpkin as you lift it from the ground. How much work do you do on the pumpkin as you carry it from the field? Okay, so go ahead and take a couple minutes to work on this one. Work on it. It's funny because that's what we're talking about. Right. Don't laugh at that, that's terrible. Okay, all right. Okay, so let's go ahead and talk about this one. So, I'm going to try to draw a pumpkin. Well, it's actually not as bad as it could possibly be. And I mean, pumpkins are supposed to be a little lumpy, right? So, there we go. So we want to take our pumpkin and we want to lift it up. Okay. Now, in order to treat this, what we can do is we can take our pumpkin and treat it like a free body diagram. So we just have a free body diagram for this. And really, the force that we're applying is going to be the normal force. But if we're lifting this at some constant velocity, what we can say then is that the sum of the forces is 0, and so the normal force is equal to the force of gravity. And as we lift this height, we can call this h. The work that we do is going to be equal to mg times the height. And so we can plug in the values for this mgh that we have here, and that's going to end up being 37.6 joules. Now, I neglected to introduce this, but joules is the unit of work, and it's also the unit of energy. So a joule is the same thing as a Newton times a meter. And so that means that this is going to be a kilogram meter squared per second squared. Okay, so that's the meaning of the unit of joules. Okay, so this is what we would have for the lifting part. And ultimately this comes down to the fact that when we look at this in terms of the FD times cosine of theta, which is really what this is, right? Because this is mg, which is the force, times the distance that's parallel to that force, right? And that's how we get this 37.6. Now, what happens if we take this pumpkin and we move it horizontally? What forces act in the horizontal direction? Forces act in the horizontal direction. It's maybe not really a trick question, but it's just 0, right? There are no forces, like if I look at this free body diagram, there's no forces acting in the x direction, right? So that means that the work done to move something horizontally is just 0, okay? All right, moving on to the next one. So next one says a 51 kilogram packing crate is pulled with a constant speed across a rough floor with a rope that is at an angle of 43.5 degrees above the horizontal. If the tension in the rope is 115 newtons, how much work is done by the rope on the crate to move it 8 meters? It's a mouthful. Okay. So go ahead and take a look at this one, and I'll give you guys a couple minutes to do it. Okay, so let's talk about this one. So what I have here is the free body diagram for this block as we're pulling it with this, instead of an F, I'll call it a T, because we told it's a tension in the problem. So what we want to do is we want to find what the work is done by this tension. And there's kind of a couple of ways to think about this, and ultimately it comes to the difference between defining the work like this, so this is FD cosine of theta, and defining it like this. Ultimately, these have to give us the same answer, but there's kind of a slightly different way to think about it. So if you use the first one, you kind of just plug things in as you go. So we say, okay, well, the force is just going to be the force 115 newtons. The distance is going to be the 8 meters. The cosine of the angle between that force and the distance is going to be cosine of 43. Okay, 43.2 or something, right? 43.5, okay. And this is just going to get written here. So that's one way to think about it. But the other way to think about it, which is equivalent to that, is to say, well, this tension is pulling up at this angle of theta, and I only want the portion of the tension that's going to be parallel to the direction of motion. And so when I look at this triangle that I have here where the tension is the hypotenuse, this side right here is t cosine of theta. So F parallel is t cosine of theta, which is 115 times cosine of 43.5 times 8 meters. Okay, and both of these, we can see they're exactly the same equation. It's just a different way to kind of conceptually think about it. Both of these are going to give us an answer of 667, or really 666 repeating, but I'm not. Anyway, and this is in joules. Okay. I wasn't the one that wrote this question, by the way, so. Okay. Do not endorse satanic imagery. Okay. So now what we want to do, it's kind of similar question. We want to think about what the net work is done on this, or the total work done on this crate as we move it this 8 meters. So this includes every force that I have here. So what is the total work done on this? There's kind of two ways to approach this. There's the easy way and the hard way, but I'll let you guys kind of discover what that is. Okay. So let's go ahead and talk about this one. Now, there's, as I kind of alluded to, there's the easy way to do this and the hard way, but it's worth seeing why the easy way and the hard way are the same thing. So let's start by looking at the free body diagram that I have here. And what we can do is we can figure out what the work is done by each force and then add them up to find what the total work is. So what we can say is that the total work is going to be equal to the work done by the tension, plus the work done by friction, plus the work done by the normal force, plus the work done by the gravitational force, mg. Okay? So right off the bat, what we can do is we can get rid of some of these terms because the force is going to be perpendicular to the direction of motion for the normal force and for the force of gravity. So these two are actually identically 0 because the cosine of the angle between the normal force is going to be 0, right? Because the angle is 90 degrees, cosine 90 is 0. Same thing for the force of gravity. Okay. So now we're kind of left with these two. We already calculated what the work was done by the tension, but we need to kind of figure out what the work is done by friction. And unfortunately, we can't explicitly calculate what the force of friction is unless we kind of reverse engineer this first, because we don't know what the coefficient of friction is. But what we can do is we can apply Newton's second law. So we could say that the sum of the forces is equal to the mass times acceleration. Sum of forces in x is going to be equal to, in this case, this is tension times the cosine of theta minus the force of friction. And this is going to be equal to something very specific. I mean, in general, it's equal to the mass times acceleration. But what do we know about this block? There's no acceleration. It moves with constant velocity. So this is 0. So what this tells me is that t cos theta is equal to minus f. Okay? So if I want to calculate what the work is done by the force of friction, this work done by the force of friction, this is equal to, yeah. This work done by the force of friction is going to be t cosine of theta times the distance, and I get an additional negative sign here because the force of friction is going to be in the opposite direction as the direction of motion. So if I add this together, what I see is from the last problem, the work done by the tension is t cosine of theta times d, and so these are going to cancel each other out. And so this is going to be equal to 0. Okay? So this was the long way to do this, but there is another way to do this, and that's to look at what the other side of the work energy theorem says. So we have work total is going to be equal to the change in kinetic energy, where the change in kinetic energy is going to be 1/2 mvf squared minus 1/2 mvi squared. What do I know about the relationship between vf and vi? They're the same. So what that means is that this difference is 0. So the total work is going to be 0. Okay? So the thing to take away from this question is, there are multiple ways to look at these kinds of problems. And occasionally, one way is going to be easier than the other, so it's good to kind of think out of the box sometimes and not just brute force the calculation. You might find an easier way to do it. Okay. So let's move on to the next one that has no question. Oh, there it is. There it is. All right. So this one says, how much work is needed for a 73 kilogram runner to accelerate from rest to 77 or 7.7 meters per second? 77 meters per second would be really fast. So go ahead and talk about this one. So let's go ahead and talk about this one. So we're told here that we have a 73 kilogram runner that's going to accelerate from rest to 7.7 meters per second. And we want to know how much work needs to be done to accelerate that runner to that speed. And so what we can do is we can say that the total work is going to be equal to the change in kinetic energy, which is going to be equal to 1/2 mvf squared minus 1/2 mvi squared. Now, since this runner is accelerating from rest, this says that this term is going to be 0 because the initial velocity is 0. Then what we can do is we can plug in our numbers. This is 1/2 times 73 kilograms times 7.7 meters per second quantity squared. Okay, and this was something I was just talking to somebody else about. But when you look at this, you could plug it into your calculator, but everybody has the capacity to get very close to the right answer without doing that. And the way that we can do that is we can kind of break it apart piece by piece. So 7.7, what's that really close to? 8. What is 8 squared? 64. 64 times 1/2 times 70. Okay. So now that we have this here, what's 1/2 of 64? 32. What's 32 very close to? 30. What is 70 times 30? 21,000. And so if you practice thinking about the math that way, you can do these kind of MCAT style problems, kind of like this one, where the answers are kind of far apart from each other, right? So if the answers here had been like 2150, 2130, 2160, then this approximation wouldn't work. But because all of these numbers are very different from each other, you can do this approximation. You can do this a lot faster than you can actually plug in numbers in the calculator if you get good at it. Okay? So let's move on to the next one. All right, so this one says 6 kilogram block initially at rest is pulled to the right along a horizontal, along a frictionless horizontal surface by a constant horizontal force of magnitude 12 newtons. Find the block's speed after it has moved through a horizontal distance of 3 meters. Okay, so let's go ahead and talk about this one. So, just kind of draw a picture to see what's going on here. So we have our block, and we're applying some force to it over some distance, and we're saying that this is going to be some distance of d. Okay? And what we'd like to do is we'd like to determine what the velocity of this block is going to be by the time it gets over to here. Okay? So this is to say that the total work is going to be equal to the change in kinetic energy. So when we draw a free body diagram here, there's only three forces acting on it. This is F, this is N, this is mg. The work done by the normal force and gravity is going to be 0, because that's perpendicular to the direction that it's going to be moving. The force that's applied here, the 12 newtons, is going to be in the same direction as the direction of motion. And so that means that the total work is just going to be equal to that force, 12 newtons, times the distance that this goes. This is 3 meters, correct? Yeah, this is 3 meters. And this is going to be equal to the change in kinetic energy. But we know that this is going to be starting from rest, and so the initial kinetic energy is 0. So this is going to be 1/2 mv squared. You can rearrange this. And then we have v is going to be equal to 2 over m, where m is going to be 6 kilograms. So 2 over 6 times 12 times 3 with a square root. This one doesn't work out as cleanly because it's got a square root if you want to approximate this. But this ends up being 3.46. Okay. But we could play our approximation game here. So if we were to do that, 12 over 6 is going to be 2. So this is 4 times 3, right? 4 times, sorry, square root of 4 times 3, square root of 12, but we can take the square root of 4, that's just 2. 2 root 3. Root 3 is 1.7, I think. So then you multiply that by 2, you get 3.4. Okay? All right. I've done this a long time. Okay. All right, so now we're going to see some real utility to using this work energy theorem. And actually, before we do this question, I want to play around with our definition of the work energy theorem and show you how we can obtain what's called conservation of energy. And conservation of energy is an extremely powerful tool in physics. You use it in classical mechanics like we are right now. You use it in electricity and magnetism, which is what you'll take next semester. You use it in quantum mechanics. You use it in general relativity. This is how we can say things like we know the energy content in the universe. We know how much dark matter there should be. That's based on conservation of energy. And so what I'm going to do is I'm going to show you how you can get conservation of energy out of this equation. Now, it turns out that if I calculate what the work is done by some force, like the force of gravity, this is going to be equal to the negative change in what we call the potential energy. So if I lift this up, okay, then gravity's doing work to get it there, and in this case it's going to be negative work because the direction of motion is opposite direction of the force. But now this has the ability to fall. It has the tendency to fall. If I'm not holding this, then it's going to fall, and that's what we call the potential energy. Now the work done by what are called conservative forces, I go into more detail on this in the video, is going to be equal to the negative change in potential energy. And so what we can do here is we can take this and we can plug it in here. If all of the forces are conservative forces, then the negative change in potential energy is equal to the change in kinetic energy. Now let's expand this out in terms of our initial state and our final state. And so this says that this is going to be negative, this is going to be negative UF minus UI is equal to KF minus KI. Now we can move this around to get all of our initials on one side and all of our finals on the other side. And so when we do that, we end up seeing that KI plus UI is equal to KF plus UF. Now we redefine this sum here to be just the total energy, which we denote as E. So this says EI is equal to EF. And this is what we call conservation of energy. So if you can find at some point, so say I have some point over here, this is like the initial point, and some final point over here. If I can calculate what the kinetic energy is at the initial point and the potential energy at this point, and add this together, and do the same thing for this point, KF, UF, then that total energy here is equal to the total energy here, provided that we're not dealing with non-conservative forces. We'll talk a little bit more about non-conservative forces next class. An example of a non-conservative force would be friction or tension or air resistance. But even in making that approximation and saying, well, we want to concern ourselves with all forces other than those, there's actually a lot of things that you can do with that. Things like Kepler's laws, so the motion of the planets is all derived from conservation of energy, and you can do that within these approximations very well. Okay, any questions about this formalism that I've laid out here? Okay, so now let's look at this question, which we did previously using purely kinematics. So what we have to do is we have to find what the equation in the x direction is for the position, equation in the y position, y direction for the position. Same thing for the velocities. We have to say the velocity at the top is 0 in the y direction. We have to go through that whole ordeal. But it's actually much simpler if we try to do this with conservation of energy. So go ahead and take a couple minutes to try to do that. Well, maybe more like 10 minutes. Okay. So let's go ahead and talk about this one. So in order to do this one, we want to consider the points where we're finding the energy for these cats. And so the first point, or the initial point, is where it's jumping from. So it's this height that it's starting at here, this 2.5 meters, and it has some initial velocity there of 4 meters per second. Now, we want to set up that equation so that we can compare that to the energy in the final state. And we know that because energy is conserved, the energy in the initial state is going to be equal to the energy in the final state. And so what we can do is we can write the energy in each state and equate them. So this is going to be our Ki plus Ui is equal to Kf plus Uf. And then expand these out. So this is going to be 1/2 mvi squared plus mghi is equal to 1/2 mvf squared plus mghf. Okay? Now, something interesting here is that we see that every single one of these terms has a mass in it. So that means that we can cancel the mass from the equation. And so what we see is that this situation is independent of the mass. So you could have a kitten, or you could have Garfield on either ends of the spectrum for the size of cats, right? So it doesn't matter what the mass of the cat is. So now that we have this equation, 1/2 vi squared plus ghi plus 1/2 vf squared plus ghf, we'd like to rearrange it to solve for what vf is. So the first thing we can do is we can move this ghf to the other side. So we have a 1/2 vi squared plus g times hi minus hf is equal to 1/2 vf squared. Multiply both sides of the equation by 2. That cancels this. That puts a 2 here. And then take a square root. And so when we do that, we end up seeing that vf is going to be equal to the square root of vi squared plus 2g times hf minus hi. And this is hi, sorry. hf, thanks. I did it on purpose to make sure everybody was paying attention. So this is what we end up having here. And when we plug in the values, we end up finding that this is going to give us an answer of 6.7 meters per second. Okay? So we're going to get quite a bit more practice with this setup, but the basic idea is you define some point where you call it the initial point. You define some point, you call it the final point. You calculate, or you set up the energy for each one of those points, you can equate them, and then you can solve for whatever it is that you need to solve for. Okay, so we got one more we're going to do, and this one is a little bit different because it involves a spring. So this one, the difference here is the potential energy that we have. So far we've talked about gravitational potential energy, but that's not the only type of potential energy you have. Another common type of potential energy we'll see this semester is the spring potential energy. And that's to say that the spring potential energy, US, is going to be equal to 1/2 kx squared, where k is the spring constant and x is the distance of displacement of the spring. Okay, so go ahead and talk about this one. So we're going to, there's an extra step in this that we haven't talked about, and that's drawing energy bar charts for this. And so the way that energy bar charts work is they're bars representing the amount of a particular type of energy that you have. And you have those in both states. Now this is meant mostly to be a tool to help you think about this, but it's not something that we're necessarily going to be grading. It just kind of helps you to think about what energy do I have in this state versus the other state, and how can I compare those. Okay, so go ahead and talk about this one. We're going to do this one. What's that? Okay, so let's go ahead and talk about this one really quickly. We're going to do a lot more practice with these on Thursday, so if this is a little cloudy, that's okay, we'll get there. So when we want to fill in our energy bar charts here, what we want to do is we want to have a bar representing each type of energy we have in the state. And so when this block is initially moving before it hits the spring, it has all kinetic energy. It's not in contact with the spring, it's not changing its height, so we're actually not interested in its gravitational potential energy. So all of the energy is going to be kinetic energy, which means that total energy is the same height as our kinetic energy bar. Now in the final state, the spring's going to compress and the block is going to come to a rest. And so that means that we no longer have any kinetic energy. We only have spring potential energy. So that's going to look like this. And again, our E total, I should make these look the same height across this, but the E total is the same as it is here. So now what we can do is we can use this in order to write our conservation of energy equation. That's just to say that the initial kinetic energy, which is going to be 1/2 mv squared, is going to be equal to the final potential energy, which is the spring potential energy. That says that this is 1/2 kx squared. Now we can cancel these 1/2s and solve for our velocity. So we see that v is going to be equal to the square root of kx squared over m. And when we plug in the values that we have here, we end up finding that this is going to be 0.95 meters per second. Okay, so that's it. So as you're leaving, go ahead and turn in your homework at the front, and I'll see you guys on Thursday.
Professor,
yes?
those